In this video, we're going to finish section 2.2, looking at some exercises from the book. Whenever you see numbers like this or this on these, that means they come from the book somewhere. So our first problem supposes that all these numbers are pairwise relatively prime. So GCD of A and B is 1, A and R, A and S, and all possible pairs are all relatively prime. And you have these two equations about their squares that hold. A squared plus B squared is R squared, and A squared minus B squared is S squared. So we want to prove that AR and S are odd, and B has to be even. So one thing we can say about the relatively prime part of this being pairwise relatively prime is that you can't have more than one of them being even, because then they would have a GCD of 2, or at least 2. So we'll say that right off the bat, since they are pairwise relatively prime, at most one of them is even. Okay. So we'll see how that helps us later on, but the rest of this is just going to be taking combinations of these equations to get some results. So let me call these equations 1 and 2. So I want to talk about adding and subtracting them. So if I were to add these two equations together, well, the b squareds cancel out, so we get 2a squared is r squared plus s squared. So the sum of the squares of r and s has to be even. So what possibilities are there? Well, if one is odd and one is even, then the sum would be odd. And if they're both even, it would be even, but that's not possible. So the only possibility left to us is that r squared and s squared are both odd. And of course, the squares, keep things. Squaring an odd number is odd, squaring an even number is even, so it doesn't change the parity. So that means r and s are both odd. All right, let's see what happens when we subtract them. So 1 minus 2 is just subtracting. This time the a squareds go away, and we get 2b squared is now r squared minus s squared. But here we can take advantage of difference of squares formula. So this is r minus s, r plus s. And we'll use the fact that we just showed that they're both odd. So that means the difference of two odd numbers is even, and the sum of two odd numbers is even. So this looks like 2 times some number times 2 times some other number. Or we get 2 factors of 2 coming into this. So now we can cancel out a 2. So we get b squared is 2mn. And so that tells us b is even. And that does it. That also shows a is odd, because remember, at most 1 is even. So from our original thing, this also shows that a has to be odd. That doesn't come from any of the equations. That just comes from the fact that they're pairwise relatively prime. So since b is even, a can't also be even. Next, we've been talking a lot in the last video about the GCD. So now we look at the LCM, or the least common multiple of two integers. And in this problem, we want to show first that there's a unique least common multiple, just like there was a unique GCD. But what we really want to do here, and kind of how the proof works, is to show a connection between common divisors and common multiples. And that should end up showing us that you have a unique least common multiple from the fact that we have a unique greatest common divisor. So suppose and say y is a common multiple of a and b. So that would mean, say, y is some multiple of a, so a times I, but it's also some multiple of b, so it's also b times some j, for some integers I and j. So it's a multiple of both. Now, I'm going to essentially map y to some value x by dividing it by the product of a and b, so ab over y. So this is going to establish a one-to-one correspondence between common multiples and common divisors. So I'm claiming that doing this gives me a common divisor. So we want to show that x is a common divisor of a and b. Well, I have two ways I can substitute for this y here. I could substitute with ai, or I could substitute with bj. So by substituting, we get that x is ab over ai. A is canceling out. I get b over I. But at the same time, I could have also substituted bj. So ab over bj. The b's cancel out this time, and I get a over j. Now with these two equations for x, I can get rid of the denominators, so this shows me that b is x times I, and a is x times j. So notice that implies that x is a common divisor of a and b. So therefore x is a common divisor. Now, maybe a picture will help here. We'll put the number line. We'll put a and b on our number line. So a and b kind of fall into both categories. They're, well, no, they don't quite. But multiples of both a and b would be, all larger. So these are, well, there's, I guess this goes. Well, we'll bound this at the top by ab. And then we'll put the common divisors down here. So this, if we think of this as a mapping, we took this common multiple over here and mapped it down to a common divisor over here. That was x. But we can see that if I picked a larger common divisor, or common multiple, then that would give me a smaller. So if I picked something larger here, dividing by that larger number gives me something smaller down here. Again, I'm not picking a common multiple bigger than AB. that would give me some fractions here. So I'm bounding my set of common multiples by the product of A and B. So let's get rid of that arrow. So that means if I take the least of these common multiples, that should correspond to the greatest of the common divisors. So since this one's unique, this map would go both ways. It would be what we call an involution. If you do it twice, it would come back to that. So it is a bijection between these numbers. So the uniqueness here would correspond to uniqueness over here. So the greatest common divisor corresponds to the least common multiple. You can make a more formal argument. Suppose you have two least common multiples, that would correspond to two greatest common divisors, which is a contradiction. But you can see that this mapping that takes AB over the common divisor to give me a common multiple, that would mean AB over the least common multiple gives me the GCD. Well, what we're trying to prove in this next problem is basically, call this thing D, call this thing M, and then multiply both sides. And you do have an absolute value issue, which I probably should have included up here. I was basically assuming A and B are all positive, but you could amend it to deal with negative numbers as well. So technically, it's the absolute value that does that. But if you consider everything to be positive numbers, then it's not really necessary. Okay. Next, we have an exercise wanting us to prove that if A and B are relatively prime, the GCD is 1, and A divides the product of B and some other number C, then A must actually divide C. Well, it certainly can't divide B, but it does turn out that A has to divide C. So how do you prove something like that? So having the GCD of 1 is a really nice sort of starting point, because that tells me that I can find a combination of A and B to actually give me 1. So A times some R plus B times some S is actually 1. And so that's for some integers R and S. Now I need to insert C in here somewhere to get a BC, so I could multiply both sides of this equation by C. So I get ARC plus, and I'll put the C there next to the B, BCS is equal to C. Now we are also assuming that A divides BC, so what does that tell us? Well, that means BC is some multiple of A, so A times some M for some integer N. So I can substitute that in for the BC that's here. So ARC, let's put that in parentheses here, plus AMS is equal to C. So just doing that substitution. And now I can see I can factor out an A. So A RC plus MS is equal to C. Well, that's exactly what we wanted to show. A times something equals C, so that means A divides C. Next, you may be familiar with Euclid's argument for having an infinite number of primes. Here we look at finding an infinite number of primes of a particular form. So primes of the form 4n minus 1, we want to also be infinite. As it turns out, primes of any sort of arithmetic progression, as long as, like if you had a an plus b or something like that, as long as a and b are relatively prime, then you'll have an infinite number of primes of that as well. But that's a lot harder to prove. So we're going to prove just this form. So if you do remember the proof for the infinite number of primes, which I believe is one of the homework problems. But in that proof, in Euclid's proof, it's by contradiction, because you can't, primes are hard to generate, so it would be difficult to demonstrate an infinite number of primes. So it's easier to say, well, suppose there are only finitely many. Suppose that there are only finitely many not primes, but primes of that form, 4n minus 1, of the form 4n minus 1. What does that really mean, that it's of that form? Because it basically means that if you were to divide it by 4, you could get a remainder of minus 1. That kind of sounds weird, but this is the same as 4n plus 3, because if you were to insert say n plus 1 in for the n here, because that would just be some other integer, you would get the 4n plus 3 here. So that would just, so it basically means that when you divide by 4, or you divide that prime by 4, you get a remainder of 3. So there's, or we're trying to show there's an infinite number of primes where that happens. When you divide by 4, you get a remainder of 3. Now, if you think about the possible remainders, leaving 2 out as a prime, the only other remainders you could get when dividing by 4 is 1. You can get a remainder of 3, or you get a remainder of 1. So let's give names to this finite number of primes of that form. So I'll say Q1, Q2, up to QR. So that's the full list of primes of the form 4n minus 1 or 4n minus 3, or 4n plus 3. Now, if you remember Euclid's argument for just having an infinite number of primes, if you had only finitely many primes, you'd multiply them all together and subtract 1, and then that presents some problems. So we do a similar thing here. We're going to let n be 4 times the multiple or product of all these primes of this form, and then subtract 1 from that. Now, when we look at how the factors that n has, notice that this is an odd number, so it doesn't have 2 as a prime factor. But it could have other odd primes. It could have one of these primes, or it could have primes of the form 4n plus 1. What we need to get our contradiction is that n has one of these primes as a factor. So kind of contradiction within contradiction here. If we suppose, for the sake of contradiction, that n contains only primes of the form 4n plus 1, then its remainder when divided by 4 will be a 1. And I'll leave that kind of as an exercise. Its remainder after dividing by 4 is a 1. And that's going to be a contradiction, because we can see that the remainder would be, well, a negative 1 or a 3. It's of the form 4n plus 3 or 4n minus 1. So this is a contradiction. So I'll just sort of put this whole thing in parentheses and leave that as a little exercise for you to show that if you have a bunch of things of the form 4n plus, so you had a bunch of these 4n plus 1, 4m plus 1, and so on, that when you multiply it out, its remainder will be a 1. Just notice that, you know, all these are 1, so you're going to get 4 times something plus 1, so the remainder would still be 1. All right, so this contradiction means at least one factor of n has the form 4n minus 1. I should say prime factor. Well, we already know what all the prime factors look like. They look like these guys. So that means n itself is some multiple, let's say a, of, say, qi, just one of those primes. But at the same time, this is equal to that. And so if I move this to the other side, I'd get a qi minus 4q1, somewhere along the line is qr, that this would be minus 1. But that's where our contradiction comes from, because on the left-hand side, we have two QIs, so we could factor that out. So we have some prime times some number is -1. That's not possible. Or, in other words, this is actually implying that QI divides -1. So that's certainly impossible. Okay, our last problem is to show that essentially that the square root of 2 is not a rational number. But we first want to show that, that this isn't possible, that you can't have two integers where p squared is 2 times q squared. So, as we usually do, suppose that it does happen. So suppose p squared is equal to 2q squared for some p and q in the integers. Now, what we're going to look at in p and q is the largest power of 2 dividing it. So we're going to let m be the largest power of 2 dividing p, and we'll do a similar thing for q. So, and q, or sorry, and m, or sorry, we just used that. So n be the largest power of 2 dividing q. So how does this help us? Well, now we know that p is 2 to the m times some, let's say, p prime, and q looks like 2 to the n times, say, some q prime, where the primes here, p prime and q prime, must be odd numbers, because if they're even, we could take another 2 out, where p prime and q prime are odd. Okay. Now, let's look at the formula that we have. So p squared is 2q squared, so we could plug these into that. So this would be 2 to the m p prime squared is 2 times 2 to the n q prime squared. Now, it probably would help us if we can pick one to be larger than the other, but it turns out not to matter too much. But let's simplify this a little bit. So this means 2 to the 2m p prime squared is equal to 2 to the 2n plus 1. If you look at the total number of 2's that are here, you get 2n here and then an extra 2 here, so 2n plus 1 q prime squared. And so one of these is bigger than, like, they can't be the same, because this is an even number, this is an odd number. So either, let's just do it this way, either 2m is bigger than 2n plus 1, or the other way, 2m is less than 2 to the n plus 1. Just put in parentheses, can't be equal, because it's an odd and even number. If they're equal, we'd have a problem, but since they can't be equal, let's take this case. So I can move this to the other side and get 2m minus 2n minus 1, p prime squared equals q prime squared. But this is greater than 0, right? So this is some power of 2. So, if it was 0, we would get just a 1 here, and then we don't get really any conclusion. But because this is a positive power of 2, we do have 2 times something equals an odd number squared. So we do get from this that 2 divides q prime, but that's not possible because q prime was odd. So that's a contradiction. And I'll leave this one as a little exercise. What do you do in that case? You just move it to the other side. So that's similar. So in either case, you're getting a contradiction. That 2 divides some odd number. So this is impossible. P squared equals 2q squared. So how do we show that that means square root of 2 is not rational? Well, now as like a separate proof here, suppose that it is. Square root of 2 is rational. That would mean that it is a fraction of 2 integers. So this implies square root of 2 is p over q for some integers, p and q. Well, I can simplify this a little bit. Multiply both sides by q, and square both sides. So 2q squared equals p squared. Well, we just showed that that was impossible. So that means square root of 2 can't be rational. Okay, so that's it for this section and this chapter. So the next video will be on chapter 3, where we finally get into the beginnings of group theory.